Hello friends, welcome to Energy is Life, and today we are going to study Introduction to Safety Engineering and the basic principles behind risk and accident prevention. Safety is not an intellectual exercise to keep us busy. It is a matter of life and death. If, during our lifetime, we can save even one life, that is an enormous achievement. History has shown us the consequences of major failures. Events such as Bhopal, Chernobyl, Piper Alpha and Flixboro remind us that accidents can affect people, equipment, property and the environment on a very large scale. The objective of safety engineering is therefore not only to respond after something goes wrong, but to prevent harmful events wherever reasonably possible. A key principle is to move safety and prevention upstream in the life cycle. A typical life cycle moves from business concept to design, then build, operation and maintenance, and finally decommissioning. The earlier we identify and control a safety problem, the easier it is to intervene and the more effective the solution can be. This is the idea behind prevention through design. Safety should be built into the system during design, rather than being treated as something to be added later. If a problem is discovered after the system is already operating, redesign or retrofit may still be possible, but intervention is usually more difficult. Before discussing risk, we need to understand the spectrum of harmful events. An incident is anything that occurs, whether desirable or undesirable. It provides a baseline for understanding operational deviation. An accident is a more serious event. It is an unfortunate and undesirable incident with a larger severity of consequence. It may result in death, injury, occupational illness, damage to equipment, or loss affecting property and the environment. A mishap represents an unexplained event associated with such harmful consequences. Not every incident becomes an accident, but every accident is an incident. We can also look at safety and health according to the time over which harm develops. Health is generally associated with long-term impact, such as chronic exposure, occupational illness and progressive degradation. Safety is more closely associated with immediate or short-term impact, such as acute events, release of kinetic energy and sudden trauma. Now let us introduce risk. Risk is an expression of both the impact and the possibility of an undesired event. In the simple model shown here, risk, represented by R, equals probability, P, multiplied by consequence, C. Probability describes the likelihood that an undesired event will occur. Consequence describes the severity of that event if it occurs. A high consequence event requires attention even when probability is low, while frequent events cannot be ignored simply because each consequence appears small. When we move from individual risk to society, the picture becomes broader. Societal risk considers the frequency and number of people who may suffer a particular level of harm. The FN curve is used to represent this relationship and to judge broad operational viability. Another useful way to understand an accident is the hazard triangle. The first part is the hazardous element. This is the source of potential harm or adverse energy. The second part is the initiating mechanism. These are the events or conditions that trigger the release of the hazardous element. The third part is the target or threat. This may be people, property, the environment, or the system that could be harmed. If these three elements come together, the hazard triangle is complete, and an accident has taken place. To prevent accidents, we need to identify the conditions that can bring these elements together. This leads us to precursors to failure. Causal factors may include unsafe acts, such as direct human errors, competency problems or violations of standard operating procedures. They may also include unsafe conditions, such as environmental or systemic weaknesses, poor safety culture or degraded materials. A diagnostic approach helps us ask basic questions: what happened? Where did it happen? When did it happen? Why did it happen? And how did it happen? This supports accident causation, prediction and classification. Now consider how risk can change over time. A system may contain a certain level of residual risk by design. But with time, energy, or function buildup, safety levels can degrade if the system does not undergo appropriate change or control. This is the central idea shown by the entropy risk model. Entropy risk can build with time. When residual risk and entropy risk together exceed the threshold risk, an accident can occur. A system that was acceptably safe at one point in time cannot automatically be assumed to remain equally safe forever. Continuous attention is necessary to recognize degradation before the threshold is crossed. The Swiss cheese model gives us another important perspective. Accidents do not usually happen because of one isolated failure. They can occur when gaps at different levels of system operation align at the same time. These gaps can involve human errors, unsafe conditions, design weaknesses, inadequate standard operating procedures, weaknesses in safety culture, or ineffective maintenance. Each layer provides a form of protection. Design safety should be built in from the beginning. Standard operating procedures should reduce variation and guide people to perform work correctly. Safety culture should create awareness, ownership, and accountability. Maintenance should ensure that systems and barriers remain effective. The objective is to prevent the gaps in these different layers from aligning and reaching the target. We can also divide controls into two broad groups: preventive controls and mitigative controls. Preventive controls act before the accident. Their purpose is to stop the accident from happening by controlling the initiating mechanisms and keeping hazards dormant. Mitigative controls act after an accident has taken place. Their purpose is to minimize the severity and damage to people, property, and the environment. Both are important, but prevention is preferable wherever it can reasonably be achieved. This brings us to ALAP, as low as reasonably practicable. The objective is not to claim that absolute safety is possible. Instead, risk should be reduced from an unacceptable level toward an acceptable level. We continue reducing risk until further reduction would require cost, time, or effort that is grossly disproportionate to the safety benefit gained. Safety is also a shared responsibility. Design engineers have the foundational responsibility for the initial facility, product, machine, or process. Operations and maintenance personnel are responsible for executing standard operating procedures and maintaining the physical integrity of the design. Organizational management is responsible for safety culture, adequate resources, and preventing competency problems. Regulatory bodies provide broader oversight through safety inspection and accident investigation. Poor design cannot simply be treated as an operational problem. Safety must be considered from the beginning. Finally, we come to continuous safety analytics. Safety analytics means using accident causation data to improve our ability to predict and prevent future accidents. Leading indicators can provide early signals that risk is building toward a threshold. Lagging indicators use information from incidents and accidents that have already occurred. By monitoring both, safety engineering can support risk-based decisions and continuously improve system performance. So, what should you remember from this entire discussion? First, safety must be engineered into the life cycle, starting with design. Second, understand the difference between an incident, an accident, and a mishap. Third, think about risk in terms of probability and consequence. Fourth, identify the hazardous element, the initiating mechanism, and the target. Fifth, look for unsafe acts and unsafe conditions before they develop into failure. Sixth, remember that risk can increase over time, so safety requires continuous attention. Seventh, use multiple layers of protection because accidents can occur when gaps across those layers align. And finally, use preventive controls, mitigative controls, and the ALAP principle to reduce risk to a practical and acceptable level. This completes our lecture 1 on safety engineering principles. Stay tuned and like and subscribe the channel for more such videos. Energy is life, and safety is what allows that energy to be used responsibly. Thank you for your time.